Hi all, I am Aparna AV. We are a team of 3 members. This is our submission to the Simulink Student Challenge 2022. So in this video, I am going to explain how we have utilized a Simulink for the design of FPGA implementation of adaptive lock-in amplifier. So lock-in amplifier is a device which can extract signals from very high noisy environment. It comes handy in many situations. Like in both channels, the input signal is mixed with we are using a dual channel lock-in amplifier with in-phase and quadrature channels. So in both channels, the input signal is mixed with a clearly generated signal of same frequency and phase as the incoming signal, and it is low pass filter. So adaptive lock-in amplifier, it works for a frequency range of 9 to 11 kilohertz and amplitude range of 0.3 to 10 volt. When we are using a normal PLL with the phase detector as the multiplier, it produces a phase error between the input signal and PLL in-phase output. That was our motivation to go for our model, that is the adaptive lock-in amplifier with QPLL, Quadrature PLL. So this Quadrature PLL uses a quadrature phase detector. It uses the concept of negative feedback to create a well-defined error, which helps in the elimination of phase error between the input signal and the VCO. So from the mathematical analysis, it is evident that the YPD or PD error, phase detector error, depends only on the well-defined error signal, not the incoming signal directly, like in the case of a PL. After doing the simulation in Simulink, we have created the simulation model in Altera DSP builder also for the hardware implementation. So this is our hardware implementation setup. We were using an FPGA, Ultra Statistic FPGA board. So the DSP builder blocks were converted into GTL code using Quadrature synthesizer, and later it was deployed into the FPGA board using JTAG. Using the DAC Intel HSLC, we were able to view the results, like we were able to compare the results of input signal versus the PLL output signal in the oscilloscope. So these are the hardware implementation results for the normal sine wave of that particular frequency range, for the sine wave with harmonics, and sine wave with additive white Gaussian noise of signal to noise ratio 10 decibels. Also, we have analyzed and see that we are getting the concept result. Next, we are moving on to Simulink demonstration. So in this, the first case, we are using the input signal as a sine wave of frequency 9.5 kilohertz. The heart of our system is the quadrature phase locked loop. So inside that, we are having the quadrature PLL. So it is using the concept of negative feedback for getting the error signal. Then we are using a moving averager. We are using a moving averager as a loop filter. The PA control is used for the fine tuning of the PLL, and VCO is also realized. This is the lock-in amplifier setup. So in this, we are using a moving averager filter instead of the low-pass filter because of its less computational complexity. So we are using a moving averager filter of the order 128. So this is the moving averager filter. Now we will move on to the results. So in this, actually two ways are there. The red color one is the incoming signal, and the green color one is the quadrature PLL generator in phase component. So if we zoom into a particular area, we can see that both of these signals are perfectly matching with respect to phase, frequency, and amplitude. So the PLL is working properly. That is evident from the figure. Likewise, we'll see the results of the lock-in amplifier output also. So this is the amplitude which is extracted, which is actually stabilizing at 0.5 volt, which is perfect. And the phase is also stabilizing at pi by 2 radians. So that is about the input as a normal sine wave. Like the next case is a noisy signal. So the additive white Gaussian noise of 10 dB SNR is added to the incoming signal. Now we will see the result. So here we can see that the PLL extracts the fundamental amount of the noisy signal perfectly, and it is matching with respect to phase and frequency. So that is evident from the figure. Next, I wanted to show the results of the output of the lock-in amplifier. The amplitude is also stabilizing at 0.5 volt, and the phase is also stabilizing at pi by 2 radian properly. It works for noisy signals properly. Now I wanted to show the difference between while using a normal PLL and using a quadrature PLL. So this is the case of a normal PLL. So in this case, the result is coming as we can see. It is evident that there is a constant phase difference between the incoming signal and the PLL output. So that is actually the reason why we have gone for the adaptive lock-in amplifier using quadrature PLL. So I have shown the results for harmonics also. So for harmonics based signal also, we are able to extract the fundamental component properly. Now we will move on to the applications. Applications means the proposed system is working in a range of 9 to 11 kilohertz, which is the VLF range, very low frequency range. It can penetrate earth, dust, etc. So geophysics can find application in this range. Likewise, it can penetrate seaboard raptors or detectors. Therefore, this can be used for the communication with submarine. Future work scope is like the frequency range of the adaptive low-gain amplifier we have designed is just 2 kilohertz. We can extend it to a higher value. We can try to extend it to a higher value. Likewise, the design can be extended for higher noise to, or better signal noise ratios, and also in different frequency ranges like high frequency, ultra high frequency, etc. So that is it about that. Thank you.